Welcome to Module 06 of the Data Center Fire Protection Masterclass. This module focuses on the systems that let people communicate, initiate an alarm, and coordinate a controlled emergency response when conditions are changing quickly. Our scope brings together 5 connected functions: voice evacuation, manual fire alarm initiation, fire intercom communication, panic alarm, and proof that each function performs as intended. The goal is controlled emergency operations, not simply alarm activation. We'll develop a voice zone matrix and define message priority logic, so the right information reaches the right areas at the right time. We'll also examine the architecture linking fire intercoms, manual call points, and panic alarm devices. The module deliverables extend beyond design. They include commissioning and evidence activities, such as C&E timing, SAT and IST scripts, inspection, testing, and maintenance records. By the end, the focus is on a system that can be operated, tested, documented, and relied on during an emergency. This module focuses on how emergency communications are controlled during a data center incident. The central idea is that communication is not simply about sending an alert. It is about establishing clear command boundaries, identifying who is authorized to act, and making sure each message produces the intended operational response. We will examine 4 communication pathways: voice, manual, intercom, and panic workflows. Each pathway serves a different function, but all must operate within a controlled emergency structure. The key principle is command discipline. The right message must reach the right people, through the right channel, at the right time. The cause and effect relationship is equally important. A notification may trigger an instruction, an escalation, a coordinated response, or a protective action. If authority, routing, or responsibility is unclear, the system can create confusion at the exact moment precision matters most. In this module, I'll connect the communication methods to their boundaries, so emergency operations remain deliberate, traceable, and life safety focused. This module focuses on purpose, audience, and the outcomes expected from studying data center fire protection communications. Its central purpose is to explain how voice alarm, fire intercom, manual call points, and panic alarm support emergency response, and how alarm inputs become the correct zone messages, overrides, communication channels, and operator actions. The key distinction is between life safety communication and security duress workflows. Both must remain visible to operations, but they should not be treated as the same event. The primary audience includes owners and operators, fire safety managers, MEP and YELV designers, fire alarm and PAVA vendors, security and BMS integrators, commissioning agents, and AHJ reviewers. By the end, participants should be able to read voice zone and priority matrices, challenge message logic and interlocks, verify intercom coverage and supervision, and build SAT and IST scripts with timing evidence. Technically, we will cover PAVA and VACIE architecture, speaker circuits, amplifier redundancy, and supervision. The data center focus includes restricted areas, data halls, plant rooms, SOC and NOC spaces, and security workflows. The module follows detection topics and precedes sprinkler and pre-action systems, connecting alarm logic to clear human action. This module focuses on the data center fire protection systems that communicate an emergency, coordinate a response, and preserve evidence that the system performed as intended. The content is organized into 5 connected areas. First, we establish system intent, applicable standards, and control boundaries, including why voice alarm, intercom, manual, and panic systems exist, and who has authority to operate them. Next, we examine the PAVA voice alarm architecture: the controller, amplifiers, speakers, message zones, and priority structure. We then move to fire intercom, manual call points, and panic or duress alarms, with attention to two-way communication and the Security Operations Center workflow. From there, we connect the equipment through cause and effect logic, covering timing, routing, interfaces, operator controls, and reset rules. Finally, we address engineering and lifecycle assurance, including design deliverables, FAT, SAT, IST, troubleshooting, drills, testing, inspection, and maintenance records. The training method is deliberately visual. Begin with the architecture, then trace priorities, zone mapping, response timing, and the evidence needed to demonstrate reliable operation. This module follows a 5-step learning path for the data center fire protection system. We begin by initiating an event, which may come from a fire detector, manual call point, panic command, or operator action. We then classify it as an alarm, duress event, intercom call, fault, or test. Next, we prioritize the response and determine whether the appropriate output is an emergency message, live page, alert, or local message. We route that communication to the fire floor, adjacent zones, plant areas, or the Security Operations Center. Finally, we prove that the system worked, using audio, intercom, event logs, timing, and reset evidence. The module outputs include the voice zone matrix, message library, PAVA and fire intercom architecture, MCP and panic workflows, timing and reset governance, and evidence checklists for testing and drills. The key review mindset is simple. Communication must be intelligible, prioritized, supervised, and commandable. A panic alarm must remain a security distress workflow, while a manual call point is a life safety input that normally bypasses investigation timers. Every voice and intercom event needs timestamped proof. This section establishes the system intent and command philosophy for life safety communication. The central principle is that different communication functions must not be confused. PAVA, intercom, manual call, and panic alarm systems support different emergency objectives, even when they share equipment or operating areas. For verified fire events, the system must convert detection into clear instructions for occupants, operators, and responders. That means delivering the right message to the right zone with the right priority. It also supports staged evacuation, all-call override, and manual firefighter command. At the same time, the system must enunciate faults, disabled zones, amplifier failures, and speaker circuit abnormalities, while preserving records of messages, operator actions, alarms, and resets. Security and operations communication follows a separate logic. Panic or duress alarms normally remain within the security workflow, while fire intercom provides supervised two-way communication at critical response points. Non-emergency paging must yield to evacuation messages and emergency microphone priority. BMS, DCM, and SOC dashboards improve awareness, but they must not override life safety command paths. These principles align with NFPA 72, EN 54-16, the IBC, and the IFC. This slide defines the performance objectives for Module 06, focused on the data center fire protection system. The design succeeds when its messages are timely, understandable, prioritized, reliable, and testable. First, instructions must be intelligible, so occupants and operators can clearly understand the action required in each zone. The system must also provide the correct response for the fire floor, adjacent floors, plant areas, and all building conditions, using the approved message for each situation. Manual command authority is another key objective. Firefighter or command microphones, along with all call functions, need clear priority and controlled access. Two-way responder communication must connect fire intercom points in important response areas back to the command center, with supervision in place. The design also separates security distress from fire response. A panic or duress signal should not trigger fire evacuation unless an approved fire event is present. Finally, the system must preserve evidence and support maintenance through audit-ready message and fault logs, test results, and drill records after handover. These objectives align with NFPA 72, NFPA 4, and IEC 60268-16. This slide establishes the command boundaries for the data center fire protection system. The central principle is one owner per command path. The FACP or FCC remains the life safety decision source, receiving initiating inputs and controlling the fire response. From there, PAVA or VACIE delivers emergency voice messages and live paging through zone speakers and interfaces. A separate path supports responder communication. Remote handsets, jacks, or call points use a supervised connection to the intercom master, where responders can select, talk, and listen. Calls, faults, and restorations should also be recorded as events. The security duress path is intentionally independent. Panic or duress inputs report to the Security Operations Center, where personnel acknowledge and verify the event, correlate it with CCTV or access information, and then dispatch or escalate a security response. The key boundary is that panic or duress does not command fire evacuation by default. For training and review, we should confirm every path against the approved drawings, point list, sequence matrix, and test records, including its owner, feedback, and reset authority. This slide establishes the standards and authority hierarchy for the fire protection system. The key principle is apply the legally adopted basis first. Local law, the authority having jurisdiction, DAMCA requirements, and adopted SNI determines statutory acceptance. From there, we use the applicable technical standards, listed equipment data, insurer guidance, and the owner's requirements. For fire alarm and emergency communication principles, NFPA 72 applies where it has been adopted. NFPA 4 supports integrated testing when multiple fire protection and life safety systems operate together. IBC, IFC, and NFPA 101 provide context for egress, emergency communication, and building response, again where adopted. The certified use of panels, amplifiers, and devices is controlled by their UL or FM listings and manufacturer manuals. For voice communication systems, YEN 54-16 and YEN 54-24, along with ISO 7240-16 and ISO 7240-19, apply when included in the contract basis. IEC 60268-16 defines STI and STIPA measurement methods, while the project threshold comes from the adopted code or specification. Finally, insurer and owner criteria address property and continuity risk, but they do not replace statutory or AHJ approval. This slide establishes a critical principle for integrated life safety systems. Command ownership must remain visible and testable. The fire event boundary includes fire detectors, ASD or VESTA, manual call points, and sprinkler water flow. These inputs report to the Fire Alarm Control Panel or Fire Command Center, which then initiates automatic PAVA messages, visual alarms, and selected building controls through approved cause and effect logic. A firefighter microphone or emergency live page may override automatic messages, but only according to defined priority rules. Reset is not automatic. It requires a confirmed safe condition and action by an authorized operator. The panic and duress boundary is intentionally separate. Panic buttons report to security or the SOC for discrete assistance and threat verification. They should not trigger fire evacuation, smoke control, or suppression. Instead, security may call up CCTV, dispatch guards, adjust access control, or escalate to authorities. If the event is linked to a fire or other life safety threat, the response follows the approved emergency plan. These boundaries should align with NFPA 72 and the owner's security SP. This slide provides the visual legend for the signal states used throughout the system. The most urgent state is red, a fire alarm. It indicates that a detector, manual call point, or water flow device requires a fire response. Red PAVA active means the public address and voice alarm system is broadcasting an automatic or manually initiated emergency message. Amber identifies an intercom call, specifically a firefighter telephone requesting two-way communication with the Fire Command Center. Teal represents a panic or duress signal sent to the Security Operations Center. This is a security distress input, and it does not trigger automatic evacuation. Yellow indicates a fault or trouble condition, such as an abnormality involving an amplifier, speaker line, microphone, or power supply. Finally, white represents a test or drill, meaning authorized zones are being exercised with notifications kept under control. Together, these colors help operators distinguish immediate fire response, emergency communication, security events, equipment problems, and planned exercises at a glance. This slide establishes the evidence basis for the example data center project. The supplied OMM and test packages provide the starting point. They document the installed baseline, intended operation, physical installation evidence, and the maintenance information needed to understand the system. That includes equipment and speaker inventories, startup and emergency paging functions, record drawings, inspections, photographs, spares, and asset data. However, documentation alone does not constitute complete acceptance. The project must add measured performance, including audibility, STIPA, ambient noise conditions, and zone coverage. It must also demonstrate electrical performance, such as circuit load and impedance, supervision, and secondary power. Just as importantly, the records need to show safe failure behavior, including amplifier or pathway faults, fallback operation, and the correct trouble indications. Finally, integrated response must be witnessed, from FACP commands and priority handling through connected outputs and system restoration. The key principle is project evidence equals document truth, field measurement, fault proof, and witnessed restoration. That combination closes performance gaps using approved scripts and records, rather than relying on assumptions or paperwork alone. This example data center project shows how the supplied PAVA OMM asset schedule becomes a practical commissioning baseline. The coverage includes an 11-story data center, with data halls from levels 2 through 9, plus a 13-story power and plant building. Each listed data hall level contains 126 racks, while plant and support areas require voice coverage as well. The schedule identifies 225 listed loudspeakers to reconcile. That inventory consists of 54 ceiling speakers, including 36 at 1.5 watts and 18 at 3 watts, 122 wallbox speakers, made up of 85 at 3 watts and 37 staircase units, and 49 horn speakers, listed at 5 watts. These figures are the starting point, not the completed test record. The next step is to turn the inventory into a zone-by-zone test list. For every speaker or circuit, the commissioning record should capture the exact location, circuit reference, tap or load setting, message tested, fault path, and supporting evidence. That structure connects the physical asset schedule to a traceable, auditable PAVA deployment. This slide establishes the installed PAVA asset baseline, with the important qualification that every quantity must be verified against the approved as-built record. The supplied OMM identifies 3 voice evacuation frames, 2 power supply managers, 6 amplifier modules, 1 remote microphone, 1 media player, 1 managed switch, and 1 39U equipment rack. The amplifier configuration is also defined, 2 300-watt modules and 4 500-watt modules. The loudspeaker count is 225 in total, made up of 54 ceiling speakers, 122 wall speakers, and 49 horn speakers. These figures are not just an inventory summary. For each item, the evidence needs to be traceable through identification, zone association, load, fault supervision, and testing. The managed switch also requires its network role and failure state to be documented, while the rack needs evidence for power, cooling, labeling, and access. The reconciliation path is straightforward, but it must be completed carefully. Compare the OMM quantity with the approved as-built, the panel database, the physical labels, and finally the witness test results. The objective is a verified, auditable baseline. This section focuses on the PAVA, or voice alarm, equipment room, which forms the audible evacuation backbone of the fire protection system. The room brings together the controller, message storage, amplifiers, standby power, and supervised speaker circuits. The key design objective is a clear, traceable chain from power and control inputs to the audio delivered in each zone. During review, I would confirm that the equipment is listed or certified under the project's adopted basis, and that priority is defined between emergency microphones, automatic messages, and routine paging. I would also verify connected load, standby amplifier capacity, ventilation, and what happens after a single failure. Speaker paths need appropriate supervision, with separation, isolation, or survivability applied where the design basis and code requirements call for it. Finally, testing should prove loss of normal power, charger or battery faults, amplifier failure, and trouble signals between the fire alarm control panel and the PAVA system. These checks align with the applicable NFPA 72, ISO 7240, and YEN 54 requirements, while ensuring faults are reported to the Fire Command Center. This section focuses on the component architecture of the PAVA and VACIE system. The central principle is that every component must have a defined function, priority, supervision method, and proof test requirement. That means we are not only identifying what each device does, but also how we confirm that it will perform when needed. The controller receives fire alarm commands and routes messages, while the emergency microphone provides the highest priority manual voice function. The automatic message player handles pre-recorded alerts, including language, zoning, and activation timing. Power amplifiers must support the required load, manage heat and overload, and provide standby changeover when applicable. The speaker circuits are monitored through lines A and B, with attention to end-of-line devices, cable routing, and single-fault behavior. Battery and DC supplies preserve operation during power loss, so autonomy, charger supervision, and replacement planning are essential. Finally, the PAVA, FACP interface and monitoring gateway must transfer status reliably, define fail and reset conditions, and support accurate, secure reporting to building and security systems. These requirements align with NFPA 72, YEN 54-16, and YEN 54-24. This slide focuses on how voice evacuation zoning should work across a multi-story data center. The key point is that messages should be mapped to approved evacuation compartments, not simply assigned by floor. A fire zone receives the approved evacuation message, while adjacent zones may receive an alert or standby message, but only when that staged approach is part of the strategy. The acoustic environment also matters. Data halls and plant rooms can have significant equipment noise or other conditions that affect intelligibility, so those areas require proof that the message can actually be understood. Stairs, lobbies, exits, and external assembly areas must then align with the approved evacuation and smoke control strategy. For training purposes, the cutaway should be read as a zoning decision, not as a universal message pattern. Every zone needs to be checked against the approved drawings, the message matrix, the smoke control strategy, and witness test evidence. In some cases, assembly or external areas may also require manual instructions. The governing context shown here is NFPA 72, along with the IBC and IFC. This slide sets out the voice zone design rules for a data center, where the audio system must support the emergency strategy rather than operate as a separate layer. The key principle is that the zone map must align with evacuation strategy, smoke control zones, security boundaries, and operating risk. In the fire floor or compartment, the evacuation message and visual alarm should match the fire alarm zone, the smoke control zone, and the intended evacuation route. Adjacent zones may receive an alert or standby message, depending on the approved emergency plan, including areas above, below, or in a neighboring compartment. Within the data hall, speaker coverage and intelligibility are especially important because of background noise, rack layouts, and containment systems. Plant and utility areas need local instructions that address hazards associated with generators, fuel, pumps, electrical equipment, and mechanical systems. Public and reception areas require clear, visitor-friendly evacuation guidance, with panic workflows kept separate. Finally, assembly or external areas may need manual live paging and safe collection point instructions. These arrangements should be coordinated with NFPA 72, IEC 60268-16, and the Project Emergency Plan. This slide defines the voice message priority stack, showing which audio sources take precedence during normal operations and emergencies. At the top is Level 1 override. This is the live emergency page, delivered through an authorized operator or firefighter microphone, with unrestricted priority. Level 2 is automatic evacuation, where pre-recorded instructions are triggered by the fire alarm control panel's cause and effect logic. Level 3, alert or standby, provides staged warning messages, supporting an orderly escalation before or around evacuation actions. Levels 4 and 5 are intended to yield when higher priority messages are active. Level 4 covers local operational paging for a specific plant or area. At the bottom, Level 5 includes general public address announcements and background music. These sources must yield to every level above them. The key concept is that emergency communication always has a clear path to the audience. Routine audio cannot compete with a live emergency page, an automatic evacuation instruction, or an alert message when those higher priority functions are active. This section focuses on the message library and operational scripts used during an emergency. The central principle is simple. Messages must be short, controlled, intelligible, and consistent with the emergency response plan. The message has to match the event and the required action. For a confirmed fire, manual call point, water flow signal, or authorized all call, the evacuation message directs people to leave through the nearest safe exit and follow staff instructions. This has the highest automatic priority, and the affected zone remains locked until reset. Alert or standby messages are more limited. They may follow a single detector, an adjacent floor event, or a staff alert, and they tell people to prepare while waiting for further instruction. Plant local messages address plant rooms or utility buildings, where local language and hazard-specific wording may be necessary. An authorized operator or firefighter can issue a logged, recorded, site-wide all-call emergency message. Security-related panic or duress advisories remain separate from fire evacuation messaging unless escalated. Finally, an all-clear or return message is never automatic. It requires fire command approval and confirmation of safe conditions, in line with NFPA 72 and the Emergency Response Plan. This slide focuses on the governance of emergency microphones and live paging. Manual announcements are powerful because they let an authorized operator give immediate, situation-specific instructions. But that power has to be controlled through access restrictions, clear priority logic, and trained operation. The emergency microphone must take priority over automatic messages, the general PA system, background music, and lower priority pages. Access may be controlled with a physical key, a password, a supervised panel state, or a defined operating procedure. Before speaking, the operator must select the correct zone, or an all-call function, unless the system is designed for emergency all-call only. Operational discipline is equally important. Poor microphone technique can create confusion, while selecting the wrong zone may leave people without instructions or trigger an unnecessary evacuation. Testing must confirm intelligibility and sound level, not merely that the microphone activates. Finally, every manual page should be logged with the operator, selected zone, time, and action taken. These practices support the governance expectations associated with NFPA 72 and YEN 54-16. This section focuses on the architecture and verification of firefighter intercom communication. The purpose is to connect the Fire Command Center with remote response points that may be separated from ordinary telephone service or isolated during an emergency. The key requirement is a supervised, two-way responder path. At the command center, the FCC master should identify the exact location being called and allow controlled talk and listen operation. At each remote point, the system must provide a clear call state and support communication in both directions. Testing also needs to go beyond simply placing a call. We need to prove supervision for open circuits, short circuits, ground faults, and abnormal handset conditions. The review should include call priority, event logging, operation on secondary power, and proper restoration after a fault. Finally, we should distinguish this system from area of refuge communication and ordinary telephony. Where the adopted code or authority having jurisdiction requires these points, every location should be tested from both ends, with evidence recorded for calls, faults, power transfer, and restoration. This section explains the design philosophy for a fire intercom system. The key distinction is that fire intercom is not a public address system. It is supervised, two-way communication intended for responders and other critical operators during an emergency. The system should be provided wherever those users may need dependable, direct communication. That includes the Fire Command Center, stair and fire lift lobbies, and firefighter lift cars where required. Depending on the approved design, it may also extend to pump and generator rooms, utility buildings, loading docks, control rooms, high-risk plant areas, and the Security Control Room, or SOC, when emergency coordination calls for a dedicated channel. Technically, the communication path needs dedicated or supervised risers, with clear fault reporting. Users should receive priority call indications and have an unambiguous talk and listen operation. Standby power must support the required minimum talk time under the adopted standard. Finally, event logs, call test records, and device labels should align with the emergency response plan. These decisions should be coordinated with NFPA 72, the IBC, and the requirements of the local authority having jurisdiction. This slide shows the communication path from the FCC master, identified here as the DVCM, to remote firefighter handsets throughout the facility. The system uses a supervised riser, which connects the master control point to remote points equipped with firefighter phones, including the FTM, one-and-jack or handset arrangements. At the FCC master, operators can control the select, talk, and listen functions. They can also see the exact location of an incoming call, which helps direct the response quickly and accurately. Each circuit supports a maximum of 2 firefighter phones, typically positioned at stair lobbies, pump rooms, and the SOC. The system also reports important conditions, including open circuits, shorts, grounds, and other abnormal states. Finally, system logging preserves the call time, detected faults, secondary power status, and restoration activity. Together, these features provide both reliable emergency communication and clear operational visibility from the master station. This slide outlines a panic or duress alarm system designed to protect people from security threats in and around the data center. The key principle is keep the security response separate from the fire command path. A duress event alone should not trigger automatic fire evacuation, smoke control, or suppression. The process begins with a discrete location-specific input. The Security Operations Center receives it as a priority event, including the exact location. Operators then correlate the signal with CCTV, access activity, and nearby alarms before dispatching guards and escalating as needed. The final step is closeout, including the incident record, device reset, and a review of lessons learned. Locations should be selected through the owner's risk policy. Examples include reception and visitor processing, the SOC or security desk, a guardhouse, loading docks, remote service areas, and critical operator positions where silent assistance is justified. Evidence should capture the input location, SOC acknowledgement, response time, correlation checks, dispatch, escalation decisions, outcomes, reset, and record retention. This supports accountability and continuous improvement without confusing a security distress event with a confirmed fire. This slide distinguishes 2 devices that may look similar, but serve fundamentally different life safety functions: a manual call point, or MCP, and a panic or duress button. The key principle is that the signal owner determines the response. An MCP belongs to the Fire Alarm Control Panel or Fire Command Center because it represents a life safety fire initiation. Its expected actions can include an immediate evacuation message, door release, and lift recall. It must not be handled as a security-only event, and investigation timers must not delay the response. Reset requires both a physical reset at the MCP and authorization through the fire alarm system. A panic or duress button, by contrast, belongs to the Security Operations Center or Security Management. It normally produces a silent alert, brings up relevant CCTV, and dispatches a guard. It must not trigger fire evacuation, suppression, or smoke control systems. Closure requires the security incident log to be closed out, along with resetting the device. Keeping these ownership boundaries clear prevents the wrong system from initiating the wrong emergency action. This slide distinguishes 2 emergency communication functions that may appear similar, but operate very differently. The first is the two-way refuge call, located in lift lobbies and evacuation stairwells. It creates a supervised bidirectional conversation, allowing people in the refuge area to both speak and listen. Importantly, the call remains active until it is answered by the FCC, so it is intended as an ongoing responder communication path rather than a momentary alarm. The second system is the disabled toilet assistance alarm, located inside ADA or disabled toilets. This is a unidirectional alarm flow. Pulling the cord triggers local audio and visual reassurance, along with an indicator over the door, so assistance can be identified at the location. The alarm is reset locally, but only after physical assistance has been provided. The key point is that this toilet alarm is not a responder talk path. One system supports supervised conversation. The other provides local notification and reassurance until someone arrives to assist. This section focuses on fire intercom operations and the call states operators must recognize. The design should clearly define how calls are initiated, prioritized, answered, logged, and restored, with each step supported by the operator SP and NFPA 72 requirements. The key principle is that every state requires both an action and evidence. In the normal state, the operator monitors the system and keeps the Fire Command Center accessible, supported by a daily or shift normal check. When a call is requested, typically by lifting a remote handset or pressing a call button, the operator connects the requested location, confirms the situation, and records the event. Priority calls from firefighter or emergency locations override non-critical calls and require a time-stamped record. Fault states require a different response. Circuit faults call for inspection and an assessment of whether impairment procedures or a fire watch are needed. Power faults require verification of standby capability, restoration of the power source, and retesting. Finally, after a call ends, the operator confirms normal status, restores the handset, and closes the event record through a reset log and operational review. This slide illustrates the timing and escalation logic for the fire protection system, from the initial event through reset. The timing shown here is illustrative only. The approved cause and effect values must replace these placeholders in the narrative, matrix, and witness test script. At T+0, an immediate event is identified, and confirmation should come through field feedback, annunciation, the audible result, and the event log. The sequence may then move through acknowledgement, an adjacent alert, and a broader response at the approved intervals, followed by reset and confirmation. Every delay, escalation, and reset rule requires documented approval and witnessed proof. For immediate events, an MCP activation, water flow signal, or confirmed fire starts the adopted response unless the approved cause and effect says otherwise. An authorized emergency microphone override is also immediate and uses the configured highest voice priority. Staged responses are different. Detector or ASD early warning may support alert, standby, or investigation stages, but only when the adopted strategy permits them. The final logic should align with the Module 04 cause and effect philosophy, NFPA 72, and NFPA 4. This section separates two inputs that can look similar at the wall, but have very different authority and consequences. A manual call point is a fire alarm input owned by the FACP or Fire Command Center. When activated, it may initiate life safety actions such as evacuation announcements, visual and audible alarms, remote fire signaling, door release, lift recall, and approved smoke control logic. It should never be treated as a security-only event or delayed as a routine fault. A panic or duress button belongs to the Security Operations Center and represents a security distress condition. Its typical responses are silent or visible alerts, CCTV call-up, guard dispatch, access control correlation, and escalation to management or police. It should not, by default, trigger evacuation, suppression, or smoke control without verified fire logic. The priority table also protects the communications hierarchy. An emergency microphone has the highest voice priority, while fire intercom supports responders and general PA remains low priority. The governing principle is simple: keep fire, security, responder, and routine communications separate, then apply NFPA 72, security procedures, and the PAVA priority table consistently. This section focuses on the interface between the Fire Alarm Control Panel, or FACP, and the Public Address and Voice Alarm System, or PAVA. The central requirement is straightforward. We must prove both sides of the safety function, that the command actually leaves the FACP, and that the intended voice output is delivered by PAVA. The command path should be clearly defined. A fire alarm input can activate a programmed message by zone or group. Manual call points, water flow, or a confirmed alarm may require an immediate evacuation message, while detector-only or aspirating smoke detection early warnings may use an alert or standby message where approved. Critically, life safety routing cannot depend on an unlisted building management system path. The interface also needs meaningful feedback. The FACP or Fire Command Center should receive indications for PAVA activity, faults, amplifier failure, speaker line faults, and power problems as appropriate. Any wiring or protocol failure should create a trouble event. Finally, message logs and testing must capture key details and demonstrate operation after losing an amplifier, a speaker circuit, or one control path, in line with NFPA 72 and YEN 54-16. This section focuses on integrating the fire protection system with security operations, building management, data center infrastructure, and remote monitoring. The central principle is separation of responsibilities. Integration improves response only when monitor-only points, security commands, and life safety commands remain clearly defined. For security operations, a panic or duress button should send both the location and priority to the SOC. A fire event may call up CCTV, notify the security desk, and place access control into its approved emergency mode. However, door release must follow the documented fire sequence, rather than an ad hoc decision by a security operator. When fire and security events overlap, their records should be linked to the fire alarm chronology. BMS and DCM platforms can receive alarm and fault status, but they remain monitor-only unless formal control approval exists. The listed Fire Alarm Control Panel, or Fire Command Center, remains the source of truth. Remote supervising stations receive fire alarm, supervisory, and trouble signals as required. Finally, synchronized time across every platform is essential for reconstructing events accurately. These practices align with NFPA 72, TIA 942, and the owner's cybersecurity policy. This slide shows how PAVA and the manual fire alarm system connect to other building responses. Voice alarm is not an isolated function. Its messages and control outputs must be coordinated through the cause and effect, or C/E matrix, so every connected system responds in the intended sequence. The key principle is coordinated, verified action. For doors, evacuation route locks and barriers release during the approved fire sequence, then relock only after an authorized reset. Turnstiles and gates must also fail safe, or release as required, to support occupant egress and responder access. Elevator recall, initiated by a manual call point or confirmed fire condition, sends elevators to the designated floor, while firefighter controls govern fire lift operation. Smoke control messaging must match the affected zone and the fire floor pressure strategy. Suppression systems require coordinated pre-discharge warnings and evacuation messages through the releasing panels. Finally, remote destinations, including the supervising station, security operations center, BMS or DCM, and operator logs, need the same event class and location. These interfaces should be designed and tested against NFPA 72, the IBC, and NFPA 4. This slide shows the early smoke detection and response workflow, from the first signal through the decision to communicate or evacuate. The key principle is that early detection does not automatically mean evacuation. First, an ASD or VESTA system detects smoke at an early threshold. That signal is then sent to the FCC or SOC, which receives the warning and begins the response process, but does not initiate evacuation at this stage. Next, an operator investigates. That may include dispatching personnel and reviewing corroborating evidence to determine whether the signal represents a genuine fire condition or requires further verification. Once the situation is understood, the FACP manages the voice response. It escalates to an alert, an evacuation message, or a live page based strictly on the approved cause and effect matrix. The rule at the bottom is especially important. A VESTA pre-alarm by itself does not trigger evacuation unless the system has been explicitly configured to do so. This staged process supports a rapid response while reducing unnecessary disruption from unverified signals. This scenario covers a fire intercom call made during an emergency response. The intercom provides responders with a protected communication path when radio or mobile coverage is unreliable, so the focus is on dependable communication between a remote location and the master panel. The sequence begins when a remote handset is lifted or a call point is activated at locations such as a stair, lobby, lift, pump room, or plant area. The FCC master panel should identify the call location and provide both audible and visual indication. The operator then selects that point and establishes two-way talk and listen communication. Where approved by the system, a priority call may override lower priority intercom activity. After the call, the handset is restored, and the system returns to normal, or records a fault if it is not properly restored. The key proof points are clear: reliable communication in both directions under emergency power. Testing should also confirm correct location labeling, reporting of circuit faults, removed handsets, and power trouble. Finally, the event log should capture call start, answer, end, and any fault or reset status, in line with NFPA 72 and the local AHJ. This section focuses on hardware resilience and how PAVA and intercom systems behave when something goes wrong. The objective is straightforward. Life safety communication must remain usable under credible single failures. First, a failed power amplifier should either transfer to standby capacity or continue serving critical zones, in line with the approved design. A dual circuit, AGB speaker line strategy limits the amount of coverage lost if one cable or loudspeaker line develops a fault. Power autonomy is equally important. Batteries or a UPS and DC supply must support emergency operation when normal power is unavailable. The system also needs continuous line monitoring, so open circuits, shorts, earth faults, and impedance drift can be detected and reported. Just as important, PAVA and fire intercom functions require local autonomy. They cannot depend on BMS, DCM, or general IT networks to perform life safety duties. Finally, manual fallback must remain possible. An emergency microphone, essential zone controls, and key indications should still be available if automation is impaired. These principles align with NFPA 72 and EN 54-16. This section focuses on the power strategy for the PAVA system, including the normal supply, batteries, standby operation, and equipment room conditions. The design must clearly identify the normal AC source, any dedicated circuits, UPS or battery backup, and dependencies on generator or emergency power. The key principle is maintaining reliable operation in both standby and full alarm conditions. That means calculating demand for the controller, amplifiers, microphones, gateways, intercom master, and remote devices, rather than sizing the supply only for normal use. The system should also supervise the charger, monitor battery condition, and announce power faults at the fire command center. Amplifier racks need adequate ventilation and heat dissipation, since thermal stress can affect reliability. Testing should confirm a transfer from normal power to standby without interrupting an active emergency message. It should verify battery autonomy under a representative alarm load, amplifier failure and standby amplifier switchover, and a controlled return to normal without restarting messages unexpectedly or silencing a fault. These requirements should be checked against NFPA 72, EN 54-16, and the manufacturer's instructions. This slide walks through a real amplifier sizing and N+1 resilience check, using the approved loudspeaker tap schedule as the starting point. First, I identify the connected load. 4 loudspeakers at 12 watts each, plus 6 at 6 watts and another 8 at 6 watts. That produces a total connected tap load of 132 watts. I then apply the project's approved 20% spare, or growth factor. Multiplying 132 watts by 1.20 gives a design load of 158.4 watts. The working amplifier must use the next listed OEM rating, so the selected unit is 200 watts. The standby check asks whether one standby module can support the largest assigned design load. Here, the comparison is 200 watts against 158.4 watts, so the preliminary calculation passes. The engineering decision is to provide one 200-watt standby module and verify automatic transfer without losing the required zones. Finally, the 20% factor is a worked project input, not an NFPA or ISO default. The final rating still depends on the tap schedule, the OEM listing, and the required resilience objective. This slide shows how I calculate the required battery capacity for a PAVA secondary power application, using standby and emergency operation demand. The governing relationship is required capacity equals the approved margin factor times the combined standby and alarm ampere hours. First, the standby term is 1.8 amps multiplied by 24 hours, producing 43.2 ampere hours. The alarm term is 12 amps multiplied by 0.25 hours, producing another 3.0 ampere hours. These currents come from the OEM load schedule and the selected emergency load, while the durations are adopted project inputs. Adding those terms gives 46.2 ampere hours. Applying the 1.25 capacity factor results in a required capacity of 57.75 ampere hours. The next listed battery bank is 24 volts and 65 ampere hours, leaving 7.25 ampere hours of calculated headroom. That is a preliminary pass, not final acceptance. I still need to verify end voltage, temperature, battery age, charger recovery, listed equipment data, and the adopted NFPA 72 or AHJ basis. The final step is a documented power failure test. This section focuses on speaker cabling, intercom risers, and the survivability of the pathways that support them. The central principle is simple. The cable design must preserve communication and report failure before an emergency exposes a hidden defect. The design should use zone speaker circuits, with line monitoring and end-of-line devices where required. Riser and branch routes need to be coordinated with fire compartments, shafts, cable trays, and fire-stopping details. Where the adopted code, the authority having jurisdiction, or the design basis requires it, pathways must be fire-rated or otherwise survivable. Cabling also needs appropriate separation from power, electromagnetic interference sources, and non-life safety communications. Field verification is just as important as the design. Labels should identify circuits at the rack, junction box, speaker, and floor riser. Before energization, record continuity, impedance, and ground fault testing. Inspect for hidden splices, unsupported cable, and unsealed penetrations. Finally, confirm that the as-built drawings match the installed speaker zones, intercom points, and manual call point or panic locations. These requirements align with NFPA 72, NFPA 70, and EN 54-16. This section focuses on proving that emergency messages can actually be heard and understood throughout the data center, not just at the speaker or in an idealized room condition. The test must represent real operating conditions and real listener positions. We begin by recording the ambient and background noise, then operate the space as planned, including normal cooling, doors, and containment. Next, we measure at representative occupied locations, including areas known to create acoustic shadows. The test also requires verification of the source level, message, and meter configuration, followed by documentation of STI or STIPA results, audibility, location, conditions, and any corrective action. The process is deliberately sequential. Establish the baseline, operate the room normally, measure the representative points, compare the results with the adopted criterion, and correct any failures. Corrections may involve speakers, racks, partitions, or HVAC, and each change requires a retest. IEC 60268-16 defines how the measurement is performed, while the adopted project code or specification determines what qualifies as a pass. This slide focuses on two acoustic challenges that affect communication in critical spaces, especially data center environments. The first is acoustic shadowing. Tall racks, cages, and cold aisle containment can physically block sound waves from ceiling-mounted speakers, creating areas where announcements or alerts are significantly less intelligible. The second challenge is high airflow noise. CRH and CRAC units, along with containment fans, generate substantial ambient noise that can mask speech even when the speaker itself is operating correctly. The key point is that acoustic performance cannot be judged from a quiet room or from a single convenient listening position. Measurements must reflect real operating conditions, with normal cooling active and doors closed. The applicable measurement standard is IEC 60268-16, using STI or STIPA methods to evaluate speech intelligibility. Testing should be performed at representative listener positions throughout the space, including locations that may be affected by racks, containment, equipment noise, or other obstructions. This approach helps confirm that critical messages remain understandable where people actually need to hear them. This section focuses on the engineering deliverables and submittal review package needed to make system review executable rather than theoretical. The central idea is traceability. Every fire scenario should connect clearly to the equipment, the message, the affected zone, and the test evidence. The voice zone matrix defines the message, trigger, priority, timing, and volume override for each zone. The PAVA schematic then shows the FACP, VACIE, amplifiers, speakers, batteries, microphones, and monitoring interfaces, with command, audio, and fault paths clearly separated. Speaker layouts need enough detail to verify coverage, intelligibility, circuit redundancy, cable routing, and power loading. The package also includes fire intercom layouts, so responders can communicate from every required location, plus MCP and panic layouts that distinguish fire workflows from security workflows. Finally, test scripts for FAT, SAT, and IST identify expected outputs, timing, evidence ownership, and reset rules. Together, these documents allow the witness to prove the complete response, not just inspect individual devices. The review basis includes NFPA 72, NFPA 4, and EN 54-16. This slide completes the PAVA commissioning test matrix. The installation reports provide useful evidence, but acceptance requires documented proof of field performance, faults, power behavior, and interfaces. The matrix starts with approved drawings, the zone and message matrix, system settings, firmware, and a baseline backup. It then verifies visual installation details, including equipment, labels, routing, separation, fire stopping, terminations, and access. Speaker circuits are checked for tap schedules, load, impedance, continuity, supervision, and isolation. Message testing confirms language, zone selection, timing, emergency microphone operation, all-call functions, and simultaneous events. Audibility testing covers ambient noise, representative locations, acoustic shadows, meter settings, and any retest map. Fault and power tests demonstrate amplifier or path failure, standby operation, AC loss, charger or battery faults, and return to normal. Interface testing covers the fire alarm panel, manual call points, smoke detection stages, doors, lifts, smoke control, and remote transmission. Finally, two-way communication, event logging, deficiencies, retesting, and restoration must be demonstrated. The witness package should include the approved script, calibrated instruments, synchronized logs, field measurements, images, and authorized closeout records. This slide defines the acceptance gates for the Module 06 fire protection systems with a clear principle: logic first, field performance second. FAP begins under controlled panel conditions. We verify message libraries, language, and priorities, then confirm zone selection and manual override. We also test amplifier, communication path, and battery faults, along with the fire alarm control panel command and feedback interface. Every result is captured in the configuration and deficiency record. Once the panel logic is accepted, SAT moves into the installed environment. Here, the focus is actual audio level and intelligibility, correct manual call point zoning and outputs, and two-way intercom operation at every point. Duress operation is checked for the required Security Operations Center response, while confirming it does not initiate a fire command. Power testing includes transfer, abnormal conditions, and authorized restoration. The witness package ties the process together, using the approved script, calibrated instruments, synchronized logs, photos or screenshots, deficiency and retest records, and documented authorized reset. This evidence supports acceptance against the reference standards. This section focuses on integrated system testing, or IST, for the data center fire protection system. The goal is not to test isolated devices, but to prove the complete response chain, from an approved scenario through system decisions, communications, interfaces, evidence, and restoration. The scenario pack covers detector or ASD activation, manual call points, clean agent pre-discharge and release messaging, zone match smoke control instructions, and two-way intercom coordination. It also includes duress events, where the expected result is a security response, with no fire evacuation. The critical principle is maintaining the boundary between life safety commands and security-only events. For every scenario, we initiate from a known source and location, confirm the FACP or FCC state, verify the correct message or intercom response, and check connected interfaces such as doors, lifts, smoke control, and remote systems. We then capture time-synchronized evidence, address any deficiency, retest, reset, and document authorized restoration. A test passes only when the expected output, field feedback, operator action, complete chronology, and restoration are all demonstrated. Security-only scenarios must also prove that unintended fire outputs did not occur. This section focuses on the inspection, testing, and maintenance lifecycle for the emergency communication system. The central principle is simple. The system must remain reliable not only at handover, but also after fit-out work, operational changes, and any modification to connected equipment. Routine IDM activities include checking the PAVA controller, microphones, message player, amplifiers, batteries, and fault indicators. We also verify speaker circuit supervision, perform sample listening tests, and revalidate intelligibility after major changes. Fire intercom handsets and jacks require call and fault reporting tests, while MCPs need both functional testing and a physical condition review. Panic alarm response drills should confirm SOC acknowledgement and produce an incident record. The other key discipline is impairment control. Any disabled message zone, amplifier, speaker circuit, intercom riser, or MCP zone is a controlled impairment. Affected stakeholders must be notified, temporary measures applied where needed, and the impairment documented from start time through restoration testing. Finally, drawings, the cause and effect matrix, and operator procedures must be updated, following the approved IDM and impairment plan under NFPA 72, Chapter 14. This slide outlines the management of change loop used whenever fire protection coverage is impaired during commissioning or readiness activities. The process begins by identifying exactly what has been lost, such as a dead amplifier. Next, the impairment is communicated to the appropriate stakeholders and formally authorized. Temporary risk controls, such as a fire watch, are then put in place while the system is being restored. The fourth step is to repair or replace the affected hardware. But restoration is not complete just because the component has been changed. We must execute both a functional retest and an integrated retest, confirming that the equipment works on its own and as part of the wider system. Finally, the panel is restored and the record is closed. The most important principle here is never normalize an impairment. A muted zone, disabled intercom, or bypass must not become the new normal. Each condition requires documented restoration, verification, and closure, so temporary measures do not quietly become permanent gaps in protection. This section focuses on fault, trouble, and abnormal condition response. The key principle is that fault response is part of resilience. A communication failure may be hidden during normal operations, but it must be identified and corrected before a fire event places the system under pressure. For an amplifier fault, I need to identify the failed unit, confirm whether the standby amplifier has taken over, and determine which speaker zones may be affected. For a speaker line fault, the response is to locate the open, short, or earth fault, then assess any loss of coverage and whether an impairment procedure is required. A microphone fault means confirming that the emergency microphone remains available, or that an alternate manual command procedure is ready. Message faults require verification of the correct file, language, priority, and schedule, with changes to control software managed carefully. For intercom faults, I check the riser, handset, jack, end-of-line device, and master panel indication, then retest after repair. Finally, panic alarm faults require checks of wiring, location, CCTV association, and security operations center event mapping, in line with the applicable standards and security procedures. This section focuses on troubleshooting and controlling false activations without weakening life safety coverage. The objective is not simply to silence a recurring problem. It is to identify the cause, correct it, and confirm that the system still performs as intended. I use a structured troubleshooting method. First, I classify the issue, whether it involves a device, wiring, amplifier, speaker line, message software, an interface, power, or an operator procedure. Before replacing equipment, I review panel and PAVA logs, SOC records, and field observations. I test the smallest affected zone first, then verify the integrated outputs before closing the issue. Every event should document the root cause, the correction, the retest, and any residual risk. False activation control requires equal care. Manual call points and panic buttons need protection from accidental operation, but they must remain accessible. Live message tests require authorized test mode, permits, and advance notification. Repeated activations and operator errors should lead to procedural improvements. A permanent bypass is never a substitute for fixing the physical or procedural cause. All actions should align with NFPA 72 and the owner's standard operating procedures. This section brings together three controls that protect long-term system readiness: critical spares, configuration control, and ready evidence. The goal is to make recovery and verification possible without relying on assumptions or improvised replacements. First, critical spares should cover the components most likely to affect continuity, including amplifier fuses and modules, standby batteries, and control link cables. These items need to be identifiable and available when they are needed. Second, configuration control ensures that the system remains aligned with its approved design. That includes approved DSP settings, localized message files, and firmware backups, all protected through strict authorized access. Without this discipline, a replacement or update could unintentionally change system behavior. Finally, ready evidence provides the reference point for future decisions. Current as-built drawings, asset registers, and FAT, SAT, and IST baseline records allow teams to compare the installed system against its approved and tested condition. Together, these controls support faster restoration, safer changes, and more confident troubleshooting over the life of the data center fire protection system. This workshop turns the Module 06 concepts into a practical, site-specific deliverable. Each participant will take one floor or protected area and build a complete communication and response matrix for it. The goal is to connect every emergency event to the right message, voice zone, priority, evidence, and control process. The work begins by selecting the protected space, such as a data hall, office, plant room, command room, stair, or external area. Participants then define the event class, identify which system owns that event, and clarify who responds. Next, they map the voice zones so routing supports both evacuation and smoke control strategy. They also assign priorities, checking that lower priority announcements or background audio cannot block life safety communication. The matrix must then define how performance will be proven, whether through audio output, STIPA, event logs, screenshots, intercom calls, or reset records. Finally, participants close the governance loop by documenting reset authority, impairment control, management of change, and training updates. The result is a usable workshop deliverable, not just a set of design assumptions. This knowledge check focuses on whether we can apply the system logic, not simply name the equipment. I'll use 6 questions to test the connections between fire protection, voice communication, supervision, and evidence. First, why must a panic or duress alarm remain separate from fire evacuation logic? The answer should address the different purposes and consequences of those signals. Next, what gives an emergency microphone priority over normal paging, and how is that priority controlled? We also need to identify the evidence that proves the correct PAVA zone received the correct message. That means thinking beyond system activation and considering verification. Then, we'll review which faults must be supervised on PAVA speaker circuits and amplifiers, including how those faults are detected. The 5th question asks where fire intercom handsets or jacks should be considered in a data center. Finally, we'll discuss when intelligibility must be retested after handover, rather than assuming the original result remains valid. The key principle is demonstrating correct system behavior with evidence, not just recognizing components. These questions align with NFPA 72, EN 54-16, and IEC 60268-16. This reference slide brings together the key abbreviations used throughout the data center fire protection module. The main purpose is to give us a common language for discussing systems, equipment, testing, and responsibilities. For voice alarm and evacuation, PAVA means public address and voice alarm, VACIE is voice alarm control and indicating equipment, and EVACS refers to the emergency voice alarm communication system. Fire alarm terminology includes FACP or FCC, meaning Fire Alarm Control Panel or Fire Command Center, and MCP, the manual call point used for manual fire alarm initiation. Operational and security terms include SOC or SMS, for Security Operations Center or Security Management System. STI and STIPA describe speech intelligibility measurement. AHJ or DAMCR identifies the authority having jurisdiction or local fire brigade. For testing and lifecycle activities, IST and SAT mean Integrated System Test and Site Acceptance Test. IDM covers inspection, testing, and maintenance, while MOC means management of change. EOL identifies an end-of-line device for supervised circuits. Finally, BMS and DCIM refer to the Building Management System and Data Center Infrastructure Management. These definitions provide the reference point for the terminology used in the remaining material. This slide brings together the primary references and governance sources for the data center fire protection system. The starting point is always local law, the requirements of the authority having jurisdiction, or AHJ and DAMCR, and the adopted SNI standards. These establish the statutory basis for the project. NFPA 72:2025 is the key reference for fire alarm systems, initiating devices, interfaces, emergency communications, and inspection, testing, and maintenance where adopted. NFPA 4 addresses integrated testing across interconnected fire protection and life safety systems, while NFPA 3 provides a commissioning framework where applicable. IBC, IFC, and NFPA 101 add context for egress and emergency communications. Product standards, including UL 864, 2572, and 2525, apply only to the selected system and its adopted use. For voice and data center applications, IEC 60268-16 defines STI and STIPA measurement methods, but not the project pass threshold. ISO EN TIA 942 insurer and owner criteria provide additional guidance. Finally, manufacturer manuals, listings, approved drawings, testing records, and O&M documentation remain the controlling project evidence. This module closes with a practical message. PAVA, Intercom, manual call, and panic alarm systems protect people only when command, priority, and evidence are clear. Voice alarm must be treated as a life safety system, not as a general public address accessory. That means defining a priority stack, from the emergency microphone and evacuation messages through alert or standby, local messages, general paging, and background music. It also means mapping fire floor, adjacent floor, plant, and all building messages with explicit timing. Fire alarm, fire intercom, and panic or duress workflows should remain separate unless an approved integration is in place. Engineering must also account for supervised single failure behavior across speaker circuits, amplifiers, power, and cabling. Operationally, staff need to know when to acknowledge, live page, use all call, reset, and close an event. Panic alarms require security response, CCTV verification, and documented closeout. Fire intercoms need call testing, fault response, and responder training. Finally, SAT, IST, and IDM records demonstrate continued reliability after changes, while every bypass, silence, or zone isolation must be documented. This module closes with 4 system integrity directives. PAVA must be treated as a life safety backbone, not as a generic public address accessory. The priority stack must remain intact. Live command takes precedence, followed by automatic evacuation, then background music. Boundaries matter as well. Panic inputs initiate security protocols. They do not automatically trigger building evacuation. Finally, every critical function must be proven with synchronized, time-stamped evidence, including audibility, intelligibility, fault handling, and integrated resets. With these controls confirmed, the system is ready for authorized closeout.